Hey guys, what's up? My name is Sreyan Bhattacharya, and today we're going to talk about a really fascinating a really fascinating topic, and that is optical fiber communications. So, this video is going to be a very short video that I'm going to cover certain topics, which are the introduction to optical fiber communications, the schematics of how things work, why it's so advantageous, and the structure of an optical fiber, the principles on which it works on, and a few theoretical terms, and I'll end it by the different types of optical fibers out there. So let's get started. So optical communications. Optical communication, which is also known as optical telecommunication, is communication at a distance using light to carry information. It can be performed visually or by using any other electronic devices. Now, an optical communication system uses a transmitter, which encodes a message into an optical signal, which is a channel, which carries the signal to its destination, and a receiver, which reproduces the message from the received optical signal. Now, when the electronic equipment is not employed, which is the receiver, is actually a person visually observing and interpreting the signal, which may be either simple or complex. So, in an optical fiber communication system, what happens is this: there's a transmitter, there's a medium to carry the signal, and there's a receiver. I'll tell you exactly how things work. So, there's an information input signal, and which is fed to a encoder, which further feeds it to a modulator driver, and then that signal is transformed into an optical source, which is then carried by a fiber medium, a transmission fiber medium, to a optical detector, which converts the signal, then amplifies it, decodes it, and the information output is produced. This is how the entire optical fiber communication system works. This is basically a schematic. Now, we'll talk about the transmission of the optical fiber communication through a medium, right? So that medium which is here, it's called an optical fiber. Now, to know what that medium is, we need to first know its structure, right? So there are basic structures of an optical fiber consists of three important parts. Number one, the core. Number two, the cladding. And number three, which is very important, is the coating or the sheath or the jacket of the optical fiber. Now we're going to talk about all these three in detail in the next slide. So the core of an optical fiber. The core of an optical fiber is also the transmission area of the fiber. It's made up of glass or plastic, and typical core diameters range from anywhere from 50 to 500 micrometers. Now we also have the cladding of an optical fiber. This is what surrounds the core and has a slightly lesser refractive index than the core. Defines the optical boundary of the core and makes sure that the total internal reflection happens at all costs. And it's also made up of either plastic or glass. Now we have the jacket of an optical fiber. This is a special plastic coating that provides shock and abrasive resistance to the fiber, and the thickness ranges from 250 to 1000 micrometers. As a matter of fact, this jacket of an optical fiber is not involved in the actual transmission of light. So this has no role to play in the communication system. It is only there to provide security, to provide protection to the fiber as it is, traversing and sending data through a vast distance. So this is just for protection. Now we come to the slide of advantages of optical fiber communications. How is this communication system so effective? We are going to find out. It has basic things. First of all, secure communication. Optical fiber communications provide a highly secure method of communication of data. That's only because no thing can actually tap into the data, and the data is absolutely encrypted and secure. Second, being the electromagnetic capability. No physical factors can deter your data, and it's completely safe of any activities occurring outside the fiber, which is the medium. Um, I think the third and the fourth points are correlated together, the speed and the distance. Optical fiber communications transfer data in a huge fraction of a second, and they provide huge speed and effectiveness and distance. So you might be thinking how the internet works, right? You're sitting here, you're searching something which is, present right at the opposite part of the globe, and you're getting results in just a minute. And that's what's fascinating. And that is the advantage of optical fiber communications. Now, what is the basic principle of optical fiber communications? It's nothing but the basic principle of light for propagation in an optical fiber. It is total internal refraction. Now, electromagnetic waves travel slowly in an optically dense medium compared to that of a rarer medium. Light propagation in a medium depends on its refractive index, which is nothing but the ratio of speed of light in a vacuum to the speed of light in the medium. Now, what's total internal refraction? My bad, total internal reflection. It is a complete reflection of a ray of light within a medium, such as water or glass, from the surrounding surfaces back into the medium. Now, this phenomenon occurs if the angle of the incidence is greater than a certain limiting angle, which is called nothing but the critical angle. And any discontinuities or any imperfections at the core cladding interface will result in refraction rather than total internal reflection. Reflection. So we can see a diagram here which shows the basic structure of the optical fiber, and we can see that we have a low refractive index cladding and the high refractive index core. And we can see that how the rays are perfectly aligned, and they are, its incidences, the phenomenon occurs, the fact that the phenomenon occurs if the angle of the incidence is greater than a certain limiting angle, which is a critical angle, and that is absolutely maintained. That's how the propagation of light takes place. Now, we come to a term called acceptance angles. We're going to talk about a few theoretical terms now. Now, what does the term acceptance angle even, mean? You can look at the term and you can find out the meaning that it's accepting a certain limit, or it's like a factor. So it's accepting this much amount of things. So we come to acceptance angles. So only the rays with a sufficiently shallow grazing angle at the core cladding interface are transmitted by total internal reflection. Hence, not all rays entering the fiber core will continue to be propagated down its length, and any rays which are incident onto the fiber core at an angle greater than QA, or let's say theta A, will be transmitted to the core cladding interface at an angle less than the critical angle and will not be totally internally reflected, which is really interesting. Thus, for rays to be transmitted by total internal reflection within the fiber core, they must be incident on the fiber core with an acceptance cone defined by the conical half angle QA, or in this case theta A. Hence, theta A or QA is the maximum angle to the axis which light may enter the fiber in order to be propagated, and is often referred to as the acceptance angle for the fiber. We can see in the diagram how the things are explained here. So there's an acceptance cone, and only if the ray of light follows or abides that cone, which is it lies inside the acceptance angle range, which is theta A, um, only then can the light be totally internally reflected. And in all other cases, the ray is going to be refracted. And hence, the optical fiber mode of communication, the principle won't be followed and the light won't be propagated. So the data won't pass, as simple it is sounds. Now, we're going to talk about something important. We're going to talk about the term numerical aperture. Now, numerical aperture of an optical system is defined as a product of the refractive index of the beam from which the light input is received and the sign of the maximum ray angle against the axis for which light can be transmitted through the system based on purely geometric considerations. Now, for the maximum incidence angle, it is demanded that the light can get through the whole system and not only through an entrance aperture. The numerical aperture, or commonly said as NA of the fiber, is the sign of maximum angle of an incident ray with respect to the fiber axis. It can be calculated from the refractive index difference between the core and the cladding, more precisely with the following relation: Na equal to n core square minus n cladding square. The numerical aperture can be given in terms of the relative refractive index difference between the core and the cladding, which is defined as delta equal to n1 square minus n2 square by 2 into n1 square, which is also equal to approximately n1 minus n2 by n1. In all, Na, or the numerical aperture, can be said as n1 into the square root of 2 into delta, which is nothing but n1 minus n2 by n1. So that's numerical aperture, and we'll be learning a lot about numerical aperture in the coming, um, you know, classes. So now we talk about the different types of optical fibers which are present out there. They can be classified according to different types of reasons. We can see all the classifications here. So these are the classifications based on materials. Optical fibers can be of glass fiber mode or like a plastic fiber mode. The glass fiber is made by fusing mixtures of metal oxides and silica glasses. Examples are GO2 and SiO2 core and SiO2 cladding. And they can also be of plastic fiber, which are made of plastic polymers and is of low cost and it's flexible, can be handled without any special care due to its toughness and durability. For example, polystyrene core and methyl methacrylate cladding. Now, classification based on number of modes are as well present there. So we'll be knowing much more about modes later on. Single mode fiber, which is also a type, is called an optical fiber designed to carry a single mode of light, which is the transverse mode. And then there's a multi-mode fiber. It's a type of optical fiber mostly used for the communication over shorter distances, such as within a building or a campus. So yeah, and then there's classification based on refractive index profile. Number one being the step index fiber. Refractive index of the core is uniform throughout and undergoes an abrupt change at the cladding boundary. And then there's graded index fiber. Core refractive index is made to vary as much as a function of the radial distance from the center of the fiber. This is also known as the inhomogeneous core fibers. So this was all about today's class, and I'm sure you have learned a lot about optical fiber communications and optical fibers in general, how they are of different types, why they are so advantageous, the basic structure, a few theoretical terms like acceptance angles and numerical aperture, and the basic principle of how things work. And this class was important because I feel like every person out there has imagined once that how the internet works and how loads and loads of data are being transferred every second. And yeah, that's been it. It's been great teaching you guys. Thank you so much for watching this.